On the surface, the SS Edmund Fitzgerald was the ultimate expression of freshwater industrial power. She was the record holder, the Queen of the Lakes, a 729-foot steel colossus designed to dominate the iron ore trade of North America. She was built to shrug off the notorious autumn gales that have turned Lake Superior into a graveyard for over 6,000 vessels. Yet, on the evening of the 10th of November, 1975, this masterpiece of naval engineering didn't just founder. She was erased. There was no frantic Mayday. There was no deployment of lifeboats. One moment, she was a distinct, solid return on a trailing ship's radar screen. 10 seconds later, she was gone, leaving only empty static and a silence that has haunted the maritime world for decades. How does a vessel of such immense displacement, manned by a veteran crew, disintegrate so instantly that there is no time to speak? The answer lies buried in the physics of the storm and the hidden vulnerabilities of her architecture. This is the story of the Edmund Fitzgerald and the engineering flaw that sealed its fate. We will dissect how it was designed and why it failed. To understand why the Edmund Fitzgerald vanished, we must first analyze the unique naval doctrine that dictated her shape. She was not an ocean-going vessel designed to ride over Atlantic swells. She was a laker, a specialized industrial machine built for a singular economic purpose: the efficient transport of iron ore from the mines of Minnesota to the steel mills of the lower lakes. The design philosophy of a Great Lakes bulk carrier is defined by strict constraints. To navigate the locks and shallow channels connecting the lakes, these ships are engineered with a box-like cross-section to maximize cargo volume within a limited draft. When the Fitzgerald launched in 1958, she was the largest vessel on the lakes, maxing out the dimensions of the existing infrastructure. But this maximization came with a significant engineering trade-off: an extreme length-to-depth ratio. While a typical ocean-going freighter might have a length-to-depth ratio of 10:1, providing substantial structural rigidity, the Fitzgerald pushed this ratio closer to 18:1. This resulted in a hull that was exceptionally long and relatively shallow. In engineering terms, this made the ship significantly more flexible. The hull was designed to flex and bento, hog, and sag as it moved through waves. On the calm waters or short chop typical of the lakes, this flexibility is a manageable, even necessary, characteristic. But in the violent, long wavelength swells of a November gale, this design trait introduces dangerous longitudinal stresses. Furthermore, the demand for maximum tonnage led to a critical reduction in internal safety redundancy. Ocean vessels typically feature transverse watertight bulkheads, dividing the cargo hold into separate compartments. If the hull is breached, flooding is contained to a single section. The Fitzgerald, however, followed standard laker design. Her massive cargo hold was a single continuous cavern, over 600 feet long. This open-hold architecture allowed for rapid loading and unloading of taconite pellets, turning the ship into a highly efficient conveyor belt of commerce. However, it also meant that the vessel lacked the citation of buoyancy protection. If the integrity of the cargo hold was compromised at any point, there were no internal walls to stop the water from rushing the entire length of the ship. She was, in essence, a single giant buoyancy tank. If that tank was breached, the margin for survival would be measured in minutes. To truly understand the physics of the disaster, we have to strip away the paint and examine the raw machinery of the Edmund Fitzgerald. When we pull up the 1,958 blueprints, we aren't looking at a traditional ship. We are looking at a massive, floating girder. The structural spine of the Fitzgerald was defined by her scantlings the dimensions of the steel framing members. At 729 feet, she was built to the absolute limits of the engineering tables of her time. The hull was constructed of welded mild steel plates, a significant innovation over the riveted hulls of the previous generation. This welding created a seamless skin, but it also changed how stresses traveled through the ship. In this 3D stress analysis, we can visualize the hull's behavior in heavy seas. The vessel was designed with a deliberate degree of elasticity. In calm waters, the keel remains flat. But in a storm, as the bow rides up a wave crest and the stern sits in a trough, the unsupported midsection sags. Conversely, when the midsection rides a crest, the bow and stern hang in the air, causing the ship to hog. This flexing is normal to a point. The Fitzgerald's extreme length meant she could deflect several inches during these cycles. However, this flexibility relied on the structural continuity of the deck, the upper flange of the girder. This brings us to the most critical and controversial component of the machine, the cargo hatches. Running down the center of the spar deck were 21 massive hatch openings, each measuring 11 by 48 feet. These were the only barrier between the lake and the 26,000 tons of iron ore in the hold. Unlike the watertight, raised coamings found on ocean freighters, the Fitzgerald utilized a low-profile, telescoping hatch cover system designed for speed. Each heavy steel cover was secured by a series of manual K-clamps, 6-8 clamps per hatch. That is a total of 1,428 manual clamps that had to be individually tightened by the crew. We can see here in the detail of the clamp assembly. A threaded bolt compresses a steel jaw against a rubber gasket. The engineering tolerance here is unforgiving. If the clamp is too loose, the gasket doesn't seal. If the coaming is damaged by the loading chutesse, common occurrence, the seal is compromised. If these hatches fail to seal, the ship loses its reserve buoyancy. Reserve buoyancy is the volume of the watertight ship above the waterline. It is the ship's life insurance. On her final voyage, the Fitzgerald was heavy. She was carrying a load of taconite pellets that put her dangerously close to her maximum draft. Modifications over her service life had allowed her load lines to be raised, meaning she sat deeper in the water than originally designed. Her freeboard, the distance from the water to the deck, was minimal. This minimal freeboard meant the deck was not just occasionally splashed. In a storm, it would be awash, effectively submerged under green water. At that point, the safety of the ship relied entirely on the integrity of those 21 hatches. Finally, we must look at the pumping capacity. The Fitzgerald was equipped with 4 7,000-gallon-per-minute electrical pumps. While impressive for moving ballast water during docking, they were mathematically insignificant against a major breach. If the hull plating cracked or a hatch failed, the inflow of water would be measured in tens of thousands of gallons per minute. The pumps could handle seepage. They could not fight the Atlantic-style fury of a superior gale. The machine was powerful, but it was brittle, optimized for calm efficiency, with a terrifyingly thin margin for error and chaos. By the afternoon of November 10th, the Edmund Fitzgerald was no longer navigating a lake. She was fighting for survival in a chaotic, fluid, dynamic environment that exceeded her design parameters. The catalyst for the disaster was the weather phenomenon known as fetch. As the low-pressure system moved across Lake Superior, the wind shifted to the northwest. This aligned perfectly with the long axis of the lake, allowing hurricane-force winds to push water uninterrupted for nearly 100 miles. Computer models of the storm state suggest waves reached heights of 35 feet, with rogue peaks potentially exceeding 45 feet. For a ship like the Fitzgerald, the danger wasn't just the height, but the wavelength. The distance between wave crests stretched to match the length of the ship itself. At 3:30 p.m., the first critical failure occurs. Captain McSorley radios the trailing ship, the Arthur M. Anderson, reporting that his ship has sustained damage. I have a fence rail down, 2 vents lost or damaged, and a list. In our forensic analysis, this is the smoking gun. The loss of fence rails indicates massive, green water, solid walls of ocean sweeping across the spar deck, but the lost vents are far more lethal. These mushroom-shaped vents connected directly to the ballast tanks and the tunnel running beneath the cargo hold. If these were sheared off, water wasn't just washing over the deck. It was pouring freely into the ship's non-cargo spaces, bypassing the pumps. The ship was now bleeding buoyancy. She was listing to port, heavier in the water, and sluggish in her response to the helm. She was losing freeboard by the minute. As darkness fell, the Fitzgerald and the Anderson were battered by a succession of massive waves. The captains described them as the Three Sisters, a triad of rogue waves moving faster and towering higher than the surrounding sea state. At 7:10 p.m., the radar of the Anderson showed the Fitzgerald 9 miles ahead. McSorley's final transmission was calm. "We are holding our own," but the physics suggest otherwise. Here is the reconstruction of the final seconds, based on the position of the wreckage. The Fitzgerald, already low in the water from flooding, encounters one of these massive rogue waves. As the stern rises on the approaching swell, the bow is driven violently downward into the trough ahead. Normally, the reserve buoyancy of the bow would push it back up, but the Fitzgerald is heavy with ore, listing, and taking on water forward. The bow does not recover. It buries itself under the mountain of water. This initiates a catastrophic chain reaction. As the bow plunges, the inertia of the 26,000 tons of taconite cargo becomes a lethal variable. The cargo is loose. As the ship angles down, the oar shifts forward, acting like a massive internal battering ram, increasing the dive angle. The ship is now operating as a submarine, but she lacks the structural integrity to withstand the pressure. The propeller, still turning, drives the ship deeper. The wreckage tells us the violence of what happened next. The ship didn't just sink, she was torn apart. The bow section hit the lake floor, 530 feet, down while the stern was likely still on the surface. The midsection, unable to support the torture of twisting and the weight of the hanging stern, disintegrated. On the surface, the Anderson's radar swept the area again. The blip was gone. There was no noise, no explosion, just a sudden absence. In a matter of seconds, 29 men and 13,000 tons of steel had been swallowed by the lake. When investigators finally reached the bottom of Lake Superior, the wreckage provided a grim, chaotic map of the disaster. The bow stands upright in the mud, while the stern lies inverted some 170 feet away. Between them lies a field of pulverized metal, disintegrated midsection. So, what ultimately sank the Edmund Fitzgerald? For decades, two competing theories have dominated the discourse. The official U.S. Coast Guard report pointed the finger at the hatch covers. Their analysis suggested that the clamps were not properly secured or had loosened under the hull's flexing, allowing water to flood the cargo hold gradually. With no watertight bulkheads to contain the ingress, the loss of buoyancy would have been invisible until the final plunge. However, many mariners and the Lake Carriers Association reject this. They point to the shoaling theory. Navigational reconstruction places the Fitzgerald dangerously close to the 6-fathom shoal earlier that evening. If the heavy ship bottomed out in a trough, it could have fractured the hull or ruptured ballast tanks, explaining the list and the reported damage to the rails and vents hours before the sinking. But when we view the tragedy through the lens of forensic engineering, the specific trigger, whether a loose hatch or a fractured keel, becomes secondary to the fundamental design flaw. The Edmund Fitzgerald was built to maximize efficiency, not survivability. The decision to construct a 729-foot vessel as a single, undivided flooding compartment created a binary state of existence. She was either perfectly intact or she was doomed. There was no redundancy. The reduction of freeboard over her career to squeeze out extra profit removed her buffer against the elements. The tragic flaw was not a single loose bolt or a navigational error. It was the Laker Doctrine itself, a philosophy that gambled the physics of a steel box against the infinite energy of a superior gale. On the 10th of November, 1975, the gamble failed. The legacy of the Fitzgerald is written in the regulations that followed. Mandatory survival suits, improved depth finders, and stricter load line limits. But the cost of that knowledge was the pride of the American side. The wreck of the Edmund Fitzgerald remains 530 feet below the surface, a silent monument to the limits of human engineering. Her story serves as a permanent reminder that while we can map the lake floor and weld steel into giants, the sea retains the final vote. In the battle between commerce and the gale always wins.